Okay, welcome back. This is now Stokes Theorem. And we can, again, just think of this as one step up from Green's theorem, the alternative form for Green's theorem. So recall that. And basically what we have is a line integral over this vector field. And we said that was equal to the double integral over this region of the curl of f dotted with this unit vector. Okay. Now, in this version, we're going to think of this in space. So if you probably don't recall, but if you do recall, this curve was in the plane, and then this region also in the plane. And now we're going to think of this curve as being a boundary of some surface. Okay, so we'll have this line integral in space over this curve C. Where that curve C is the boundary of this surface that we're integrating over here. So the thing we're integrating is the curl dotted with the unit normal vector ds. All right, so first we want to convince you of kind of verify, right? So the first couple exercises in the book, again, they want you to verify the theorem. You may want to do this like once or twice, but after that, just pick whichever one's the easiest. In this case, unlike the last problem, it's kind of easy whichever way you do it. So let's look at number 5. And we're given a vector field. In space. And then we're given a surface, which is one of these elliptic paraboloids. And just the region over top of the xy plane. So z greater than or equal to 0. So in the xy plane, if you let z equal 0, for that you would get a circle with radius 3. And right, so what did it look like? It's one of these things in the XYZ plane. Okay, so in order to first pull off the line integral, we need to parameterize this surface. Okay, so right, let's say that then to do this line integral, I guess it's not the surface we even need. We just need this, the boundary, and the boundary is in the xy plane. So yeah, this problem isn't as hard as some of the other problems could be, where you're so we can almost let the z part of our equation just be 0. So I'll say r of theta is equal to, and we're thinking of generating this curve here, but in space, but it's just kind of generic because the z component is 0. But in general, for circles, if you remember, hopefully you've done some of these in the past day or so, but if not, it's going to be for a radius of 3 cosine theta, 3 sine theta, and then the z component is just 0. And we're going to let theta vary from 0 to 2 pi to generate the entire circle. Okay, so we're having to then reparameterize this line integral, or this rather, the line integral over the vector field, or reparameterizing in terms of theta. And so for the vector field itself, inside, I'm replacing all the y and z with this material here, right? So this is now my x, this is my y, this is my z. So negative y plus z, negative y is negative 3 sine theta, z is 0. X minus z will be 3 cosine theta, and then x minus y is 3 cosine theta minus 3 sine theta. Sorry if I went off the page. And then we want to dot that with, and remember how this works. This dr part we're going to replace with the derivative of r with respect to theta times d theta. Right. So I need the derivative of this part. So take the derivative of the components, and you get negative 3 sine theta, then 3 cosine theta, and then 0 d theta, and we're integrating from 0 to 2 pi to pull off this line integral. So doing the dot product, it's going to simplify real nice. You'll get 9 sine squared theta plus 9 cosine squared theta plus 0, okay, d theta. And then this part, of course, is just equal to 9 because of the Pythagorean identities. We can factor out the 9 d theta, and then it's just 9 theta evaluated from 0 to 2 pi, which is equal to 18 pi. Okay. So in this case, the integral wasn't that hard, but in general, these space curves can be kind of nasty. Okay, we just got lucky such that the boundary of this surface isn't completely in the xy plane. Okay, so let's try the other side then, double integral of the curl, and see what happens there. See if that's I think this will be a little bit worse because you have to do the cross product to get the curl, the cross product operation, the NAMBLA F thing. I think that's the way they wrote it. The upside down triangle is a NAMBLA. Okay, so anyways, now we're on to this other side of the equation where we're doing this double integral over the surface of the curl of f dotted with the unit normal vector. Okay, so I need this object here, this curl part. So the curl of f is this NAMBLA dotted with f. So you're applying the gradient kind of to the vector field. And the way we thought of that was kind of to set up this determinant operation where the first set of components were partials. Okay. Okay, and then we need the vector field here. I've lost my vector field. Negative y plus z. I'm going to have to smush it in, I apologize. X minus z, and then x minus y. Okay, so, cover up the appropriate places. Partial of this with respect to y is negative 1, minus the partial of this with respect to z, so minus negative 1 is plus 1. Okay, so that'll be a 0. And then negative, so cover up the middle column, you do partial with respect to x of that is 1, minus partial with respect to z of that is 1, so that'll be 0 as well. And then cover up, the last parts, and you get partial with respect to x is 1, minus the partial with respect to y of that is negative 1, so at least that one's non-zero. So what do we get? 0, 0, 1 minus negative 1, of course, is 2. Okay, so then I'm going to have to kind of get this normal vector thing for the surface. So where is my formula for the surface? So that's the elliptic paraboloid thing, right? So where the heck is it? It's z equals 9 minus x squared minus y squared. I'm going to set it equal to 0 to get the gradient, because that's kind of what we need for this normal vector, and then there would have been that cancellation, or it will turn into a double integral over a region. Okay, so z plus x squared plus y squared minus 9 is our big G function. So this is big G of x, y, z. And then we need the normal of this for the dot product inside of this thing here. Okay, so, or rather, we need the gradient of that thing. So the gradient of G is 2x, 2y, and then 1. Okay? And then that's our double integral. And now it'll be over a region, and that region was that circle with radius 3. So I just put that for reference there. This point is 3, 0. I'm going to go polar eventually, so I'm not going to bother with the limits just yet. I need to get the curl thing, that was 0, 0, 2 in this case, dotted with the normal, but that's kind of like using the gradient. So 2x, 2y, and then 1, and then dA. And then the dot product is just 0 plus 0 plus 2 dA. And then I want to go polar. So I'll have the double integral of r dr d theta from r equals, well, the equation of this in polar coordinates is 3, right? And then I need to go theta equals 0 to pi, to 2 pi rather. So 0 to 3, and then 0 to 2 pi. And so let's get at it. The integral of r is r squared over 2, so I can factor out 1/2, and I got the integral of r squared from 0 to 3, and d theta. So that'll be 9 minus 0, so 9/2 times the integral of d theta, and then the integral of d theta is just theta, so 9/2 theta from 0 to 2 pi, plug in the 2 pi, and you get, crap, you get 9 pi. That's not our answer, is it? Is that the answer? I thought it was like 18 pi. Yeah, I screwed something up probably. Yeah, it's supposed to be 18 pi. What the heck did I screw up? Did I forget my 2? Yeah, I forgot the 2 back here. Okay, sorry about that. So there should have been a 2 out here. And then this would have been 1. And then this would have been 9. And then this would have been 9. So this would be 18. Sorry about that. But you get the answer, same answer either way you do it. So it's a way of checking your answer for one thing, if nothing else. Okay, let's do one more of these. And in this other case, it should become more clear why you would choose to do the double integral over the line integral. Because in this case, the curve is going to be in space as opposed to a plane. So number 15 then, just in general, using Stokes, the vector field here is more annoying. So we get negative ln of the square root of x squared plus y squared. Then arctan of x over y, and then 1. And our surface is another one of these elliptic paraboloids. So 9 minus, no, it's just a plane. I take that back, sorry. But the weird thing is we're integrating over this region, and it's given by a polar equation, my first octant only. Okay, so it's basically this surface, but over this region and the first octant. So I kind of want to figure out what this region is in the xy plane, and then I'm going to kind of graph this over top of it so you can see what it looks like. Okay, so that's my first objective. Let's just figure out, what we're dealing with. Right, so first get this thing drawn. So r equals 2 sine of 2 theta. Okay, so here the amplitude is 2, and then I'll go after the period. So wedge 2 theta in between 2 pi and 0, divide by 2. Theta is in between pi and 0. And then I could section that off into 4 parts, so going by pi over 4s will give me 1 complete cycle. Right, so amplitude 2, it's going like that, and then back down, and then back up. So in the XY plane, then, we'll have some helper circles, and then some angles at pi over 4s. I just want the first quadrant because I'm just working in the first octant. Okay? So anyways, starting at 0 and then at pi over 4, it's going to increase to 2. So it'll look like this. And then from pi over 4 to pi over 2, so from here to here, I got that first part. And then from here to here, it's going to decrease back to 0. Okay, so it'll decrease back to 0. And what you're ending up with is a rose. This is just one particular petal of that rose. And we're integrating over that petal. Okay. Okay. So in the x, y, z space, then this surface we can figure out by doing the intercept of the axes method. So, and the on the x-axis, you just let y and z be equal to 0, and so our formula I should have wrote z equals. Sorry. Okay, so if you let z and y equals 0, you get 2x minus, or 9 minus 2x is 0. And then add 2x over and divide by 2, so x equals 9 halves. In other words, you're going to be at 4.5 on the x-axis. And the y-axis, then what are we doing? Letting x and z equal 0, so you'll get 3y equals 9, and then divide by 3, so you just get 3. And then on the z-axis, letting x and y equal 0, you get z is 9. Okay? Okay, so what does this mean with respect to kind of putting it all together? Well, 1, 2, 3 is out here. 1, 2, 3, 4.5. Sorry. So we're going to have this diagonal on the xy plane, and then over top of it, so let me draw it. Okay, so here's the XYZ space. And we have this rose petal in this plane, but on the z-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, it's way up here. On the x-axis, 1, 2, 3, 4, 5, it's 4.5. On the y-axis, 1, 2, 3. So we have this plane and that first octant cutting through like that. And it's over top of this rose petal. This line right here corresponds to this line right here. Okay. So that red petal is going to be inside of that triangle, like in this region here. And then we just want to work with the surface that is bounded by this region that lies on this bigger triangle here. So it would look something, I'll get a different color, like this on that surface. Okay? It's this region here that we're looking for basically the circulation around. Okay, okay. So I would need a space curve for that thing, which is quite the annoyance, right? I'm not going to be able to pull that off. So it's easier then, in this case, to work with the double integral over this polar region here, this red region. Okay, okay. So in order to pull that off, I need the curl, and you'll need then also the gradient of this surface to do your dot product. Right. So let's get the curl first, I suppose. So the curl of f, again, it's this operation that's kind of like a determinant. Okay. And this one is fairly annoying. Just because of the nature of the components. There's a little bit you could do. For instance, use the natural log rule to rewrite this. Because we're in that first octant, you're never going to have any sort of issues with changing or doing the power rule for the logs or something like that. I believe. I'm just talking off the top of my head. But you could, rewrite this as 1/2 and then bring the 1/2 out in front. So that'll make life a little bit easier. So negative 1/2 ln of x squared plus y squared. And then the second component, arctan of x over y. And the third component is 1. Then get your curl. Okay, so cover up these parts. Partial with respect to y of that is 0. Partial with respect to z of this. There's no z variable, so that'll also be 0. Cover up these parts. So the partial of that with respect to x is 0. Partial of that with respect to z, there's no z variable, so that's also 0. So that's nice. And then finally, the last part does contribute information. Okay, so with respect to x, this thing will be 1 all over 1 plus u squared times the derivative of u, right? So our u is x over y. So 1 plus x over y squared times the derivative of x over y, and we're doing it with respect to x. Okay, so that'll be 1 over y. And then plus, or in this case it'll not be minus because this term is negative, the partial derivative of this with respect to y. So it's 1 all over, and there's that negative 1/2 in front, so I still have to have this negative 1/2 times 1 all over the guts, right? So that'd be x squared plus y squared times the derivative of the guts. So the derivative of x squared plus y squared is going to be, with respect to y this time, is just going to be 0 plus 2y, so 2y. Okay, this cleans up pretty well. In particular, I just want to take a quick peek-see at this guy and see what happens there. So what do I have? I have 1 all over 1 plus x squared over y squared times y. Okay? And what I'm going to do is multiply top and bottom by y squared. Okay. Okay. First things first, this y will divide into that y squared, leaving you with 1y up in top. Okay. Okay, so I'll have y up in the top, and then I have y squared times this sum. Right? So you'll have y squared times 1, which is y squared, and then y squared times x squared over y squared is that y squares will cancel, and you just have x squared. Right? Okay, so that's what this mess is. So we're having our vector field is 0, 0, this mess, which we found to be y all over y squared plus x squared, and then minus, rather, this should end up being a plus, right? Because it's always this minus this, and because it was already negative, this will be plus. Okay? So if you remember, when you do the determinant for that component, it's always going to be this partial minus this partial. Okay, but if I do a minus of this partial, this is already negative, so it'll become a positive right here. Okay, sorry about that. Okay, so with this term, the 2's will cancel, and you'll again get y over x squared plus y squared, or vice versa. Okay. In other words, you're going to have 2 of these in your third component, and finally our curl of f is 0, 0, 2y all over x squared plus y squared. Okay. Okay, what else do I need? I also need that normal vector, which I'm going to get kind of from the gradient of this thing, but I got to convert it into that g function, right? This g of x, y, z thing. So g of x, y, z is going to be z plus 2x plus 3y minus 9. Sorry, I went off the page again. Z plus 2x plus 3y minus 9. And then the gradient of that, which is going to kind of serve as my normal vector, will be 2, comma 3, comma 1. With respect to x, it's just 2. With respect to y, it's just 3. With respect to z, 1. Okay. Now, finally, I'm ready for my integral. So I have this double integral over this polar region, which the book usually calls a D, of the dot product of our curl with this gradient vector, and then dA. Okay. I'm going to have to reparameterize everything. So it's a polar integral. So for that red region that I'm integrating over, I'm integrating from r equals 0 to r equals 2 sine 2 theta. The dot product is going to be just 0 plus 0 plus 2y over x squared plus y squared, which I can rewrite. Okay? So one thing at a time, I guess. I'm going to go from 0 to 2 sine 2 theta. And then on the outer integral, I'm going from 0 to however far I had to go in order to get that pedal, right? So in order to get the pedal, I had to go from 0 to 2 pi over 4, which is pi over 2. Okay, so 0 to pi over 2. Right, so inside here then I'll have 2y over x squared plus y squared, but 2y in terms of polar coordinates is 2r sine theta. X squared plus y squared is r squared, and then I have to multiply it by r dr d theta. Okay. And then look, the r times r is r squared. That will cancel with that r squared, and I'll have, and this should be a sine 2 theta. No, it's just sine theta, sorry. Ugh. All right, so then that will be the double integral of 2 sine theta dr d theta. And then I got to integrate that, right? So this is the, we can factor out the 2 if we wish. So 2 times the integral of sine. The integral of sine is negative cosine theta, d theta. And I have to evaluate that from 0 to 2 sine 2 theta. Okay. Whoops, so I'm with respect to r, so I screwed that up. Sorry about that. This is why you don't use pen. The single integral now of, if I factor out the 2, this would be r times sine theta. I'm so sorry. And then I evaluate that from 0 to 2 sine 2 theta of d theta. Okay. All right. Plugging in the 2 sine 2 theta, we get 2 times the integral of 2 sine 2 theta times sine theta d theta, and then minus 0. I'm going to use a trig identity to simplify that 2 theta thing. Okay. So I'll rewrite 2 sine 2 theta as, what can I rewrite it as? Cosine theta sine theta. 2 cosine theta sine theta. So it's this part that I'm rewriting using that identity. Sine 2 theta is equal to 2 sine theta cosine theta. Okay, and then it'll just be 4, a factor of 4 there times 2, so there's a factor of 8 in front of the integral. And then I have sine squared cosine theta d theta. And then I can do a u sub, so let u equal sine theta, and then du will just be this cosine theta d theta. Okay. So I'll end up with 8 times the integral of u squared du, and then integrate that. So you have 8 times u cubed over 3 back substituting, I get 8 thirds times sine cubed theta from 0 to pi over 2. Sine of pi over 2 is 1, so 1 cubed is 1, so this will be 8 thirds minus sine of 0. Sine of 0 is 0. 0 cubed is 0 times 8 thirds is 0, so you just get 8 thirds. Okay, right, so that's what you're going to be looking at in terms of integration. One little mistake, you know, you're in a world of hurt. Okay, now we want to actually get a physical interpretation for what curl is. And what we mean by this is curl at a point. Okay, it's not necessarily that we're looking for an interpretation of Stokes. But I mean, for Stokes, I would intuitively kind of think of it as maybe a summation of all of the circulation over a region, and that's somehow equal to the circulation around the boundary. Okay, so maybe that's what the integral is about, but we just want to know the physical interpretation of curl at a point, and we're going to be able to get our hands on that from the from Stokes' theorem itself. So physical interpretation the way you think of curl at a point is really again, you're going to have this vector field doing whatever. So maybe that's part of my vector field. I don't know, and then there's vectors all over the place, right? And you can go around in some spots, but maybe we just care about the vector, the curl at that point there. Okay, so what you can kind of do is draw a lasso around it or draw a loop around it, and the curl is kind of the measure of the alignment between the unit tangent vectors and the force field. Okay, and the way to interpret it is maybe think of the circle having little paddles on it, right? And the force vectors are kind of hitting those paddles depending on where they're aligned, and that will cause movement in a circular direction, especially in this case, because you kind of have this force field pushing, this force vector pushing against this little paddle. These are kind of in the same direction, so there's no movement. But this little force vector is definitely pushing against, say, this paddle right here. Okay, so if you have a circular region and you can, you know, in that circular region, on that circular region, there's this idea of tangent vectors, and what you're doing is measuring the alignment between the tangent vectors and the force field, right? So maybe the force vectors are going like this. You can kind of see they're really in alignment with those tangent vectors. And when that happens, it'll cause a rotation in this direction. Okay. Okay, so that's the in my opinion, the physical interpretation. If you go into if you go into the Khan videos and stuff like that, they'll talk about it in terms of the partial derivatives of the components of the vector field, which is a great way to think of it too, and I advise you to go look at it. But our book is looking at getting their hands on this interpretation via Stokes' theorem itself. So note, or rather, let's say, consider basically a small disk. So last time we were considering a sphere. Now we're going to consider a small disk, call it S sub alpha, at some point x, y, z on our surface. Okay. So for instance, we have our usual elliptic paraboloid here. And you can consider a little disk on this thing, right? And maybe even give it the counterclockwise rotation there. Okay, and what we're trying to define is the curl at this particular point. We'll do it by kind of letting the radius of this disk, this alpha value, go to 0. Okay, so from Stokes, we can say that the line integral of this vector field, kind of dotted with the unit tangent vector, which is another way of writing our usual line integral over this vector field. From Stokes, we could say that's equivalent to the double integral over this disk. Okay, so this C sub alpha would be the boundary of this disk, and this S sub alpha is the disk itself. Okay. All right, so this turns into the double integral of the curl of the vector field and that disk dotted with the normal vector. And for a small enough disk, and given that it has some sort of continuity, so the values aren't jumping out at you, there's none of that business. Continuous means it's kind of in a very small region, it's nicely behaved. So in that case, I believe that's what they kind of then mean. So in that case, you could factor that whole thing out as a constant. And from there, we can get our definition for curl, right? So if you factor this all out, curl of f at this point, x sub 0, y sub 0, z sub 0, dotted with this normal unit normal vector, this leftover integral is just going to be a surface area of that disk. And we know the surface area of a circle is basically just equal to 2 pi r, which in this case r is alpha. So you'll have curl of f at this point, dotted with this unit tangent vector at that point, times 2 times pi times alpha. Okay? Or is it area? Sorry. So yeah, crap. This should be area here, pi r squared. So pi alpha squared. Sorry about that. All right. So anyways, I was thinking circumference, but we're dealing with the area of that circle. Okay, so this would represent the area of that little circular region here, which is just pi r squared, not 2 pi r. All right, so anyways, we get this formula, and from then you can get your formula for curl by kind of just dividing both sides of this equation by the pi alpha squared. So the book is going to define curl of the vector field at a point to equal the line integral about of a circle about that point divided by this pi alpha squared, where we're taking the limit of the radius going to 0. So you get another one of these kind of limit definitions for a characteristic at a point. The way you want to think of this thing, though, in the big picture from what the people at Khan Academy tell me, because I'm not really a physics person, I've never studied like Maxwell's equations or anything like that. The way they want you to think of it is a matter of rotation. Okay, and in the book, you know, they're going to say it's the rotation of the vector field about this normal vector. Okay, so the book says rotation of the force field about some unit normal vector. But I think in the beginning, if nothing else, think strictly in terms of a two-dimensional force field, and you're kind of putting a number on the amount of rotation that maybe a disk would feel being induced by a force field that is kind of pushing on the sides of that disk in a way, in kind of this way. All right. So if you imagine you had force field pushing on this disk, pushing right here, pushing right here, and pushing right here, the overall effect to the disk is going to be this rotation. Okay. Okay. So let's look at one more problem. And I did come across this, although I'm not a physics person. I used to like to go to the library at CSU, which was an awesome library. I don't know how awesome it is anymore. But back in the day, you could go in there, and like on the fourth floor in there, just tons and tons of books, and you could look at people's master's theses and their PhD theses. And one of them I looked at was some guy had written his whole thesis on the circulation of water and coffee, on cooling coffee, and it was just seemed extremely crazy at the time. I mean, I was just studying multivariable calculus at that point, but here somebody had dedicated an entire book to this idea, and this example kind of is like seeing the curling effects of the top of the water at the top of a coffee mug, I guess, or the coffee at the top of the coffee mug. So anyway, example 3 from the old book is kind of the deal. So what you have is, literally a coffee cup. In this case, it's a cylinder. And then you're trying to figure out the curl at the top of this coffee mug. Or, well, for us, it won't be the curl. It'll be the, we want to know this double integral, right? We want to figure out the double integral of S of, I'm butchering this, I'm sorry, of, this is my last video, and this, I'm butchering it, I apologize. We want to figure out the double integral of curl dotted with n ds, okay? Okay, so they're not giving you a vector field in space. So in the book I was reading, the thesis I was reading when I was an undergrad, he was looking at, or maybe it was a she, I don't remember, she or he was looking at the coffee liquid in space. And we're just going to look at the top of the coffee here and consider that for our integral. So the vector field they're giving us to work with is this thing, which is not very nice, but life is like that. So negative y times square root of x squared plus y squared plus x times the square root of x squared plus y squared. Sorry, this would be the second component. Right there. Okay. Right, so we want to figure out, do they give us an equation or anything? They're saying that the cylinder has a radius of 2. Okay. And apparently maybe the height is at 2. I'm reading the book. Scrolling around, cylinder container of radius 2, and its motion is given by this thing. S is the upper surface. Okay, so this is not dependent on the height anyway, so I don't have to worry about that. But this is a cylinder of radius 2. So at least in the xy plane, I can get a formula there if I need it. It'll be x squared plus y squared equals 4 in the xy plane. All right, then. So let's go at it and figure out this integral. So I need the curl, and this should be the curl of the vector field. Right. Okay, so IJK, all that business. So negative y square root of x squared plus y squared, and then x square root of x squared plus y squared, and then z is 0. Oops, and we're taking partials of those. Okay, so I did not write that, but alrighty then. So first part 0, 0. Second part 0, 0. And then the third part will give us information. So the partial of this thing with respect to x minus the partial of that thing with respect to y. So first this guy, partial of that thing, I'm going to need a product rule. So with respect to x, 1 times the square root of x squared plus y squared, plus then leave x alone and take the derivative of the other part, the square root of x squared plus y squared. So bring down the 1/2, and then you have x squared plus y squared to the negative 1/2 times the derivative of the inner part, which will be, with respect to x, that'll be 2x. So that's equal to the square root of x squared plus y squared. I keep going off the page like 50 million times. I apologize. And then this junk would be x squared all over the square root of x squared plus y squared. Okay. When you take the derivative of this part with respect to y, you get pretty much the same thing, right? Let's take a look at what we get. So for the first part, we got that thing. For the second part, with respect to y, I'll have negative square root of x squared plus y squared, and then minus y times 1/2 times x squared plus y squared to the negative 1/2 times 2y. So I'll end up with negative square root x squared plus y squared minus then y squared all over square root of x squared plus y squared. All right, this will clean up kind of well. First off, noting when I add, or rather I'm subtracting, right? I have to subtract this and this. So I'll have 2 of these. And then with this and this part, you have a common denominator already. So all you're doing is adding up x squared plus y squared. And you'll have x squared plus y squared to the first power over x squared plus y squared to the 1/2 power. So that plus that will give you x squared plus y squared to the 1/2 power. And then you already have 2 of those from here, so you end up with 3 square roots x squared plus y squares. Okay, so all these generally will have a nice little simplification, usually, but you know. All right, so anyways, then what do we do? Then I need to integrate this thing. I also need that normal vector, and the normal vector, the outward pointing vector for this thing, we should know that's just going to be this unit vector here, which is 0, 0, 1. Okay. Okay, so our dot product of the curl with that, 0, 0, 1 with dot product with this is just going to give us this third component. So it'll just be 3 times the square root of x squared plus y squared over this region in the xy plane, which is this region here. So we're going to go polar for this. Okay, so I have the double integral from 0 to r equals 2, and then from 0 to 2 pi of 3 times the square root of r squared, which would be r, and then r dr d theta, so I end up with r squared dr d theta. Okay. And then that will equal the integral of 3r cubed over 3, which would just be r cubed from 0 to 2 d theta. So you have 8 times the integral d theta, and then the integral of d theta is just theta from 0 to 2 pi. So it looks like we're getting 16 pi again. Seems like a common theme today, 16 pi. All right. So that should do it for section 15.8. So now if you get really ambitious, you can go and study fluid flow inside of your coffee and maybe write your PhD thesis on it, or at least your master's thesis, right? Okay, wish you well. Bye-bye.